Draw a mechanism for the reaction of bromine with butene and name the product. So butene looks like this. Now if we remember, it's monkeys eat peanut butter. So 1, 2, 3, 4 carbons there. So we need a carbon chain that's 4 carbons long. And on the second carbon, 1, 2, we got the double bond. And we put another carbon up there. So that's butene, like that. And we've got to do the mechanism with bromine. So we've got our bromine molecule, Br2, that approaches the double bond. Now the double bond is rich in electrons, in negative charge. So the shared pair of electrons here between the two bromines will be repelled by this negative charge as that bromine approaches. So the shared pair of electrons are going to move in that direction towards this bromine. So this one ends up with a partial negative charge and this one ends up with a partial positive charge, like that. Normally in bromine, of course, because the two atoms have the same electronegativity, there's no overall dipole, permanent dipole. But here a dipole has been induced by that negative charge on that double bond there, which has pushed the electrons towards this bromine, like that. Now that bromine there with the partial positive charge can act as a electrophile, so something that can accept a pair of electrons. So the pair of electrons from this double bond move to this electron deficient bromine, and the electrons from this bond here move to this bromine here. So in our next step then, we end up with because that breaks by heterolytic fission, and so does that one. So these bonds are breaking by heterolytic fission, which means the two electrons move, not just one, but there's two. So it always leaves a charged species. So we'll end up with a negatively charged bromide ion, and we got the carbocation, which is a positively charged carbon molecule like this. Then, because you can see what's happened there, that bond is sprung open and it's left that without an electron, because it was sharing its electron with this one, but now it's lost an electron, so it becomes positively charged. And now this bromide ion can now form a bond with this positively charged carbon atom. So then the final step in our mechanism looks like this. So that's our product there. So it says draw the mechanism, which we've done, for the reaction of bromine with butene and name the product formed. Well, we've got 1, 2, 3, 4 carbons. So it's but, and there's no double bond, so it's not butene anymore. It's an alkane. Well, it's a halogenoalkane, so it's an ane, butane. Now the bromines are in positions 2 and 3. That's position 1, 2, 3. So we say 2, 3. We separate the digits with a comma, and we separate the digits from the letters with a hyphen. So we got 2, 3 dibromo. 2, 3 dibromobutane is our product there. Right now then, consider the reactions of hydrogen chloride with butanene, hydrogen bromide with 2-methylpropene. In each case, draw the structure of the two possible carbocation intermediates. So let's do the first one up here first then. So we've got butanene. So this means the double bonds on the first carbon. Being but means there's 4 carbons in our chain. So we can do this. And then we can say CH2, CH3. Rather than draw out all the bonds individually, we can do that. So we've got 1, 2, 3, 4 carbons in our chain, and the double bond is on position 1, on carbon 1 there. And we got to think about if it's reacting with hydrogen chloride, like that, what's going to happen? So this has got a permanent dipole. That's partially positive, that's partially negative. You know, halogens are very electronegative elements, and they will pull the charge away from the hydrogen and leave that electron deficient. And then that's the electrophile. That can accept the electrons. So there's going to be 2 possible carbocation intermediates with this, because the molecule isn't symmetrical around this double bond. If this had a CH2, CH3 over here, it would be symmetrical and we wouldn't get 2 products. But as it is, we've got a hydrogen over here and we've got a CH2, CH3 over here. So it's not symmetrical around the double bond. So we are going to get 2 products, and we're going to get 2 possible carbocation intermediates. Now the first one, what's going to happen then is this bond, the electrons from this bond are going to jump towards this electron deficient hydrogen, and the electrons in this bond are going to move towards the chlorine to form a chloride ion. So our 2 possible intermediates are where the bond springs open like this, and we get the hydrogen, this hydrogen forming here, joining here, and then we're left with the positive charge on this carbon in the intermediate, like that. And then you see we're going to have our chloride ion there that's going to add on to there. So that's one of our intermediates. The other intermediate will be where the hydrogen adds on to the other carbon. It will add on to this one, and that will leave this one here with the positive charge, like that. And then the chloride ion is going to add on to this one. So those are our 2 carbocation intermediates. You can see they're different. One of them has the positive charge on position 2, the other one's got it on position 1, and it's just because these electrons can move in different ways. You can have the electrons forming from this carbon to this hydrogen, which happens here, or between this one and this one, which happens here. So we've done that for the first one then. Let's go on and answer the questions for this one, and then we'll work out the hydrogen bromide one. So explain which carbocation is the more stable. And in this case, the one that's going to be the more stable is going to be this one. And that's because this has got a methyl group here, which is going to push negative charge onto that positive carbon. And it's also got an ethyl or an alkyl group here that can push negative charge on. So in 2 places, it's got negative charge being pushed on, and it helps stabilize that positive charge. So it's not as positive as it could be because it's having charge being pushed onto it. Whereas if we have a look at this one, we've only got one alkyl group that's pushing charge on, because then we've got 2 hydrogens here that are attached to that carbon with a positive charge. Here we had 2 alkyl groups pushing charge onto there. Here we've got 1 alkyl group just pushing charge on. So this one is the more stable. And write the displayed formula and name the major product. So the major product, this is the most stable intermediate, and therefore that's going to create the one with the major product. So what's going to happen is then that chlorine is going to add on there, and so we're going to end up this is the major product. Now when we can check that is by applying Markovnikov's rule, which says the hydrogen that's being added on, which is this one, adds on to the carbon that's already got the most hydrogens. So this carbon has 1 hydrogen, this one has 2 hydrogens bonded to it. So the hydrogen is going to add on to this one because it's already got the most hydrogens to it. So that works out. The Markovnikov rule follows, and it also makes sense in terms of the stability of the carbocation intermediate. write the displayed formula and name the major product. Right, here we go then. So we've got 1, 2, 3, 4 carbons in the chain. So it's some kind of butane. There's no double bond there, so it's an halogenoalkane. And the chlorine is on position 2. So what we'd say is it's 2-chlorobutane is the major product. And the minor product would be 1-chlorobutane, because it would add on to this point. Right, now we'll move on to this next one here then, for a hydrogen bromide with 2-methylpropene. Let's just get rid of that. And we'll do the same, hopefully, with this one. So the first thing I'm going to do is I'm going to write 2-methylpropene. So I'm going to put my double bond horizontal because that makes it easy. And we've got propene first of all. It'd be like that, wouldn't it? It would be 3 carbons and there'd be a double bond there. And what it's saying is on position 2 there's a methyl group. So 1, 2, there's a methyl group here like that. So that would be our 2-methylpropene. And it's reacting with hydrogen bromide, which, as before, the halogen is going to have the partial negative charge, the hydrogen the partial positive charge. So in our mechanism, that bond is going to spring open, and that bond, the electrons from that bond are going to move to the bromine to form a bromide ion. So our 2 intermediates, and we're going to get 2 carbocation intermediates because it's not symmetrical around the double bond. We've got 2 hydrogens over here and CH3 over here, so it's not completely symmetrical around that double bond. So the double bond could spring open like this, and we could have the hydrogen adding on here like that, and the carbocation then ends up on this carbon. The positive charge ends up on this carbon, and we'd have our bromide ion that's just about to add on to there like that. Our other intermediate then will be the other way around. The hydrogen's going to add on to this carbon like this, and it's going to leave the positive charge on this carbon, carbon 1 here, and the bromide will then add on to this one. So draw the structure of the 2 possible carbocation intermediates. So that's one of them with the positive charge on carbon 2, and that's the other one with the positive charge on carbon 1. It just all depends how these electrons move to form the bond. They can form a bond here, or they can form the bond there and leave that one positive. So that's the way. Explain which carbocation is the more stable. So we're looking for the one that's got the most alkyl groups pushing charge onto the carbon with a positive charge. Now, if we have a look at this one, we've got a methyl group here pushing negative charge on. We've got a methyl group here pushing negative charge on, and a methyl group here pushing negative charge on. On this one, we've just got this kind of alkyl group here that's pushing negative charge on. 2 hydrogens here are not pushing negative charge on. So the more stable one is going to be this one, because we've got negative charge being pushed on in 3 directions. Here it's just 1. So that's the most stable. So this one's going to form the major product. So the electrons from that bromide are going to move there. And so we're going to end up with this thing here like this. We've got to name it as well. So our longest carbon chain is 1, 2, 3, whichever way we look at it. 1, 2, 3 that way, 1, 2, 3 that way. So it's going to be some kind of propane. Monkeys eat peanut butter. So monkeys eat peanut butter. So it's going to be propane. We've got to say where the position of the groups are. Now, if we have a look on position 2, we've got the bromine, so it's going to be 2-bromo. But also on position 2, we've got a methyl group. So we're going to have 2-methyl. So those are our prefixes. Now, which one will come first? Do we say 2-methyl, 2-bromo, or do we say 2-bromo, 2-methyl? We do it in alphabetical order. So the bromine comes before the methyl. So in our full name then, we'll go 2-bromo. Now we have to put a hyphen because we're separating our letters from our numbers. 2-methyl. And then we've got propane like that. 2-methyl, 2-bromo, 2-methyl propane. Right, move on to the next one. So here we are. Propene reacts with bromine in the presence of sodium chloride. This is an interesting one. I quite like this one. In the presence of sodium chloride, a mixture of products is formed. Explain why the mixture contains, and it's given some things there. So let's work out what's going to happen then when propene reacts with bromine and there's some sodium chloride present. Let's work that out. So we'll start off first of all with our propene, which has 3 carbons in the chain. Monkeys eat peanut butter. So we've got our propene there, and then we've got our bromine. There's going to be a dipole induced. That's going to be partially negative. That's going to be partially positive because the electrons from this electron-rich double bond are going to push the electrons that way and create this induced dipole. And the electrons from here are going to form a bond here, and the electrons from here, or this bond here, is going to break by heterolytic fission to leave this negatively charged like that. So in terms of our intermediates then, we could have the double bond springing open like this, and the bromine adding on there, and then the positive charge ending up on carbon 2. And we got the bromide ion there ready to add on. We could end up with the hydrogen adding on, or sorry, the bromine adding on here to begin with, and the positive charge being on here on position 1 on carbon 1. So those are the 2 intermediates that we could end up with. Now when they react and you form the product, so when this bond here forms here and when this bond forms here, but we're going to end up with, in both cases, this thing here. So we're going to have a bromine there, we're going to have a bromine there. It's a different case to when we had something like hydrogen bromides, because we'd have a hydrogen in one place and a bromine in another, but now we've got bromine in both places. So we end up with this product here, which is 1, 2, actually the comma shouldn't be there, dibromo, 1, 2, 3, propane, like that. Now do we say, we do end up with 1, 2 dibromo propane, right, that makes sense. Now, so why do we get other products then? Why is it talking about 1-bromo, 2-chloropropane and 2-bromo, 1-chloropropane? Where's this coming from then, if we're reacting bromine with our propane like that? Because we've just done the mechanism and we see we end up with this single product. Why are we getting other stuff? Well, the clue is we've got sodium chloride there. So in amongst all this, we have got some chloride ion here like this, floating around. So when we get this point here with our carbocation intermediates, we've got some chloride ions that can jump onto here. So the electrons from the chloride can jump on here and jump on here like this. So we will end up with this product here, where the chloride, or the chlorine is added on there, and we will also end up with the chlorine adding on to here from this intermediate. So we're going to end up with this. And let's name these products then. So here we've got the chlorine in position 2 and the bromine in position 1. So we will have 1 bromo, and then it's 2 chloro propane. And on here we've got 2 bromo. Remember, we put the bromine before the chlorine because it's alphabetical order. 1 chloro, the chlorine's on position 1, propane. So is that what it says? It says more of 1 bromo, we got more of that, bromo 2 chloropropane, than 2 bromo 1 chloropropane. So we've got more of this and that, and we've got to explain why. Wow. It comes down to the stability of the intermediate again. If we have a look at this intermediate, which is where this 1 bromo 2 chloropropanes come from, we've got an alkyl group over here pushing negative charge on there, and an alkyl group, a methyl group here, pushing negative charge on. So the negative charge is being pushed on in 2 places from the alkyl groups. If we have a look over here, it's only being pushed on in 1 place from the alkyl group. Here we've got the hydrogens that are not pushing on negative charge. It's only the alkyl groups that push negative charge on. So that's the most stable intermediate, and that's going to produce the major product. So we're going to get more of that than that. Now it says, why do we get 1,2-dibromopropane? Why are we getting this, but no 1,2-dichloro? Why are we not getting one with chlorines both there? Well, the chloride that's around, remember it's chloride, sodium chloride that's in there, it's not chlorine. So the thing that's happening there at the start, at step 1 of the mechanism, where we're getting the electrophile, which is bromine, attacking that double bond, that can't happen with a chloride because there's no partial positive charge to accept that electrons. A chloride ion that's already negatively charged isn't going to accept more negative charge. You need something that's electron deficient to act as an electrophile. So the bromine's the electrophile in this case, and that can accept the pair of electrons there from the double bond, but the chloride is not an electrophile. So that's not going to happen there.